All right, grade 10s. I've had some coffee, I've had some chocolate. I think I'm ready to go on this afternoon's lesson on potential energy. Okay, so we just got off talking about kinetic energy, which is the energy of motion. Now we're going to turn our attention to potential energy. Now, potential energy is defined as the energy possessed by an object as a result of its position or condition. It actually comes in a variety of kinds. We're going to spend most of this chapter discussing gravitational potential energy. Now, this is energy, again, due to an object's position above whatever in physics we're going to decide is our zero mark. And again, in physics, we get to often decide that, right? So, because if I had my position, for example, my position, I am standing on the floor, however, of my demo desk here, but then my demo desk is higher than the actual floor of my classroom. So I have a different amount of gravitational potential energy based on how high I am above the ground. Okay, so again, it's sort of a reference point idea because it's all about position. There's other forms of potential energy, including elastic potential energy, which is energy stored due to something being compressed or something being stretched, like a rubber band, of course, for example, or a spring. Chemical potential energy is found in all forms of matter. So, for example, we could take gasoline, for example. So it is stored energy that a car ultimately wants, and the way we get at that energy, of course, is use a chemical reaction. So if a chemical reaction is involved and chemical bonds are involved, then we're affecting an object's chemical potential energy. Even food, like whatever you have for lunch, is providing your body with energy. It's releasing that energy, but it was stored in the actual food itself. And then we have nuclear potential energy, and this is energy that is stored in the nuclei of atoms. Remember, atoms are full of protons. Protons do not like each other. They want to repel from each other. And so that nucleus just has a whole bunch of pent-up energy, keeping those protons confined. And of course, if we can release that, if we can split that nucleus, we would actually release a lot of that energy, which is how nuclear bombs work, or nuclear power plants for that matter. Now, this slide is kind of getting all into exactly what I just said. So you can have a little look at that yourself in the slideshow. I'd also recommend you to watch, I believe in the Google Classroom, you will find a link in the video clips to a SciShow that goes through each of the different forms of potential energy. Now, we're going to focus on gravitational potential energy, and we're going to be able to do calculations based on it. So remember, this is energy that is possessed by an object due to its position above some kind of ground state. And in the ground level or ground state is usually assumed to be zero gravitational potential energy. We only gain or have potential energy if we are at some height above whatever we've determined zero to be. Quite often, the ground is going to be our zero mark, okay? And as we lift an object above that zero mark, we are saying that it's gaining gravitational potential energy. So again, we look at a couple of examples here. You guys know I like soccer, or football, as it's really called. If we had a soccer ball that was one height above the ground, we would say that it has gravitational potential energy if we consider the ground to be our zero mark. And so that energy is now stored in the ball. Now, we could get that energy, we could transform that energy when the ball starts to fall back towards the ground. It would be releasing that gravitational potential energy, and it would essentially exchange that energy, or that energy would be transformed from potential to kinetic as it falls. Remember our laws of thermodynamics? Energy is neither created nor destroyed, but it can change form from one to another. So as this ball falls, it will be converting its stored potential energy into kinetic energy, and then it can even do work because of the relationship between mechanical energy and work, or kinetic energy and work. And we'll talk more about that later, and we talk more about that in chapter 6. Okay? Yeah, and we're kind of talking about work down here in the last bullet here. All right? If we want to store potential energy in an object, we have to do work on that object, right? So if I had a coffee mug, or a thermal, and I do have a coffee mug, of course, because I love my coffee, right? So I have my coffee mug here. If I assume the bottom of your screen is my 0, I'm gonna give my mug gravitational potential energy by me doing work on the mug. So I'm lifting the mug. That's work done by me. Remember, a force through a distance. Well, now that work is stored as gravitational potential energy in the cup. More examples. Lifting your bag, school bag, to the top of your table. What could we say about that? Well, we've increased the gravitational potential energy of that bag. Now, what if we lift the same bag on the moon? What happens to its gravitational potential energy? Would it be 0? Would we increase, or would we decrease its gravitational potential energy? Well, again, we would be increasing its gravitational potential energy. But would the gravitational potential energy be the same on Earth compared to the moon? Would that cup, or bag in this case, have the same, I'm fixated on the cup of coffee. Would it be the same? Well, the answer is the same, less on the moon, or more on the moon. Well, the answer is that it would be less. There would be less gravitational potential energy stored because you would have done less work, because there's less gravity on the moon compared to the Earth. So the moon is about 1/6 the size of the Earth, so that means there's about 1/6 the amount of gravity, so you would only be doing about 1/6 the amount of work. So gravitational potential energy does depend on the force of gravity that there is. Okay? And now, when we get to actually calculating gravitational potential energy, we need a formula. Now, remember that the kinetic energy formula, it's based on the 2 factors that affect kinetic energy, which is the mass of that object and its speed. When we look at gravitational potential energy, there are 3 factors that determine an object's gravitational potential energy. Number 1, its mass. Number 2, the field of gravity, the gravitational constant, the gravitational acceleration. Remember that the force of gravity accelerates objects. So we call that, it's a constant. Remember when we talked about acceleration, we said that gravity accelerates you at a constant value of 9.81 meters per second squared. So that's a constant based here on the Earth. So when you're working with this formula, we use the symbol G, and it's going to be a constant of 9.81 meters per second squared. And then, of course, the gravitational potential energy depends on the height above your ground zero. Looking at our units, we know that energy, no matter what form of energy it is, its units are going to be joules. We are going to want to continue to use kilograms as our base unit of mass. The gravitational constant is meters per second squared because it's an acceleration, and the height needs to be in meters. So we need those units to make this formula work. All right? And here we can see that constant at the bottom of the screen. So we've got some examples. So examples, let's say you lifted a set of books which had a mass of 3 kilograms, and you lifted it a height of 2 meters. What is the gravitational potential energy gained by the books? Again, we're going to assume G is 9.81, or we can round it to 10 perhaps for this question, because our significant digits are not very large. We're just using some whole numbers here. So again, straightforward algebra question. MGH is our formula. So that's mass of 3 times the constant times the height. We get an answer of 60 joules. Now, as a work energy theorem question, okay, what would be the work done by you to lift the books up to that height of 2 meters. Well, ladies and gentlemen, I hope you understand that it's the same, right? We've simply transformed our work into the gravitational potential energy of the books. It is stored in that form, all right? Again, force, if you might remember from middle school, is mass times acceleration, ma, but remember we're working with gravity, so you can see that actually the work formula, force times distance, and since force is mass times some kind of acceleration, we actually get the same formula. And it's going to be the same answer of 60 joules. All right, that's just a proof. And I'm not really going to have you doing that on a quiz or a test, but this is just a mathematical proof for why your work is equal to that gain of gravitational potential energy. Again, guys, a slide about the work-energy theorem, that they are connected. If an object gains energy, then we say that positive work is done. So gravity tends to do positive work on falling objects, since falling objects are gaining kinetic energy. So a gain of energy means that positive work was done. So gravity actually does work on falling objects. Now, if an object loses energy, we say that negative work is done. Now, in the case of a kinetic energy situation, brakes take energy away from moving objects. So we would say that a car's brakes do negative work, okay? All right, and that's true for potential energy as well. So for example, if you did 50 joules of work pushing a swing, that 50 joules of work becomes the kinetic energy of this child on the swing. But then of course that swing starts to go higher. So there's a transformation of the kinetic energy into the gravitational potential energy of the swing. And then it eventually stops. So it's all been converted to gravitational potential energy. And then of course that swing, and then we're going to have that swing start to be pulled down by gravity and change that gravitational potential energy back into a form of kinetic energy. Okay? Now we're assuming that there's no air resistance, and we're not losing any energy into air resistance or friction, which generates heat. Remember, the energy can't just disappear, it gets transformed from one form to another. Okay, let's actually work a couple of problems here. All right, so if we did 565 joules of work on a 12 kilogram box by carrying it up a flight of stairs, how high is the flight of stairs? Now, so again, sometimes we like to have a picture. So there is our flight of stairs, and we're doing 565 joules of work. We know that the mass of the box that we are carrying is 12 kilograms. We want to know how high in meters is the flight of stairs. Okay? Now, important thing to realize here, folks, is that when we talk about height, this is a vertical height. Like the height is actually this height right here. From where you start to where you finish. So very much like displacement that we talked about earlier in this chapter. Even though our motion is to carry the box diagonally up a flight of stairs, all we really care about is the height from where the box is to where it started from, vertical distance, straight line, vertical distance. So this is the height that we're finding here, all right? Okay. So now what we want to realize is that this work has become gravitational potential energy. That's an energy transformation that's occurred. So that's going to allow us to use our gravitational potential energy formula, remember, which is mgh. But we're solving for h. So we can either rearrange our formula, or we can substitute, simplify, and solve. For this case, I'm going to rearrange the formula so that h is equal to the gravitational potential energy divided by the mass times the gravitational constant. Then I'm going to substitute in my values. So I'm just going to continue that over here. GPE, 565 joules, divided by the mass, which is 12 kilograms. And remember, our constant might not tell you in the question, but G is a constant value of 9.81, right? So when we ultimately do that on our calculators, let's grab a calculator here. So when we ultimately do this on our calculator, watch your order of operations, guys, depending on your calculators. Okay, you can either do this, you've got to put this in brackets on the bottom. Okay, otherwise you will get the wrong answer if you're trying to do it all in one step, but you can, of course, simplify and do more steps. So I get an answer rounded to two, I'm going to round it to 2 decimal places of 4.8. My answer is going to be meters. Now again, if I just want one digits, no, I was given 2 digits in my question, so having 2 digits in my answer is kind of what I'm looking for. So this height right here is 4.8 meters, not the diagonal, the vertical line there. So that was how high that flight of stairs was. So hopefully that makes sense. Okay, let's do another problem. This time we have a boulder on a ledge. The dreaded boulder. There's a lot in physics. There's a lot of boulders on ledges that are waiting to fall. All right, and it says that it's 36 meters above a lake. So there's our lake, 36 meters to the bottom of the lake. The boulder has 28 kilojoules of gravitational potential energy. All right, so I can go, hey, my GPE is equal to 28 kilojoules of energy. We know that the height is 36 meters, and we are trying to find the mass of the boulder. Okay, and remember that the mass is going to be in kilograms, but it implies that I'm working with joules. Remember that in the formula, we work with joules, so why don't we just take a second to change 28 kilojoules into joules. So remember, that's a factor of 1,000, because there's 1,000 joules in a kilojoule. So this needs to be 28,000 joules. There, I have all my values. So again, we can start with our formula. So remember our formula, gravitational potential energy. Now guys, quite often, I write gravitational potential energy as EP. Just like kinetic energy is E with a little k, I quite often do GPE as E with a P for potential energy, and that's equal to mgh. This time I'm solving for m. So if I rearrange my formula for n, I divide gh from both sides. So m is going to equal the potential energy divided by g times h. So if I carry on to the left here, gravitational potential energy is 28,000 divided by, remember G is 9.81, it's our constant, multiplied by the height is 36 meters. So we're going to get our answer in kilograms. So trusty calculator, okay, 28,000 divided by, now in brackets, I'm putting what's in the denominator there, 9.81 times 36 equals 79. How many digits? Probably just want 2 digits. So 79 would be a good, so guys, that's 79 kilograms. Probably not a terribly big boulder, but there we go. We find the mass of this boulder sitting on the ledge waiting to fall on some unsuspecting canoeist that's on the lake. All right, so you better be careful. Okay, so that's that kind of a problem. And that's the end of chapter 5, guys. So again, happy calculating of gravitational potential energy.